So everyone's here. Hello, everybody. Thank you for joining today. So this is our third webinar at Wiser, and it's the first time we're doing it a little later, as we wanted to also accommodate everybody in the United States in the afternoon, as previously our events were our afternoon in Europe, which were early mornings. So we're really happy that people from all over the world are joining us today. So today's topic is rethinking energy demand forecasting with quantum machine learning, a use case that was done between Wiser and Eon. And so first, a bit about Wiser. So Wiser has existed for multiple years, so for many, almost 10 years, but we were called Womanium previously. So we have trained over 75,000 scholars globally from across 120 countries. We've done 20 industry projects, including the one today that's being presented. We have 53 active quantum research fellows, and we work with 85 plus quantum providers and strategic partners. So our verticals are quantum ecosystems such as Colorado. So we're part of the ecosystem in the US and also in India, in Andhra Pradesh. And we do self-paced learnings. We have our research arm, which is exactly those projects that we do with partners such as Eon. And we have our summer program now, which we just completed another edition. And now the challenges are being assessed. And finally, we have our insider program for startups. So starting, I'm going to introduce our speakers. So first, we have Dr. Corey O'Meara, Chief Quantum Scientist at Eon Digital Technology, who leads quantum technology initiatives in the energy sector. So he's going to be one of our key speakers who's going to present about Eon, but also one of the sections of the project. Next, we have, just get to the next slide, Mackinson. We have Mackinson Bullshit, a quantum applications research scientist at the University of Guadalajara, whose work focuses on quantum computing, AI, and energy forecasting. And we have finally Aditi Lal, a quantum computing developer and researcher at Wiser, specializing in quantum algorithms and machine. So I will pass it on now to Mackinson, who will get things started.
Good morning, good afternoon, everyone. My name is Mackinson. I'm a research fellow at Wiser. Thank you again for joining us today in this webinar that's about using quantum machine learning for energy demand forecasting. Let's introduce our agenda today. And first, we will give an introduction about the project. And after that, exploring the quantum machine learning method that you use in this project for energy forecasting. After that, we look for the future perspective research insight for this project. And finally, we get our conclusions and we open for discussion or question we have about this webinar. So during this webinar, we learn how to use quantum machine learning. In this case, we use quantum reservoir computing and quantum Gaussian process to forecasting energy demand. And also we learn how you can validate possible quantum advantage and real world data set. So now I will invite Dr. Corey that will introduce the quantum project and our collaboration with Eon and this project.
Yeah, thanks, Mackinson. Yeah, perfect. Okay, so I wanted to set the stage to explain to you all sort of how the project came to be and essentially the kind of domain background about why we're investigating this. So I work at a company called Eon. We're one of the largest multinational utilities in Europe, operating in 15 different countries. So we provide energy and gas to almost 50 million customers across Europe. And we also have a grid business where we monitor and manage about 1.6 million kilometers of power line in Europe. And in Germany alone, we also manage about 1 million renewable energy assets, which are all connected to the energy grid. And this video on the right-hand side of the screen is showing real data. This is real over a 24-hour period. In red, you see the different postal code or the different areas in the northern part of Germany. And the color code is energy demand that's feeding in to local neighborhoods. And this is also what you see in the embedded graphic where you have this kind of graph. So down below each node of this graph, you can think of as a house or a building in red, showing the energy demand changing. And then you also see that there's these yellow circles, which is renewable energy generation. And so, throughout the day, as the sun rises, we have more renewable energy flowing into the electrical grid. And it is a game, a very complicated game and very important game, given the age of AI we're all in now, is to balance the supply and demand of electricity. And that's actually what the grid frequency is, if you've ever wondered what that is. And the challenge is that the electrical grid is not a digital thing natively, right? This has been built up over many decades. We've all seen power lines. You probably don't give much thought to them, besides when your energy goes out or you have to pay your energy bill, right? And what we're doing is we're digitalizing the grid in order to make use of all of this renewable energy. As we move through this energy transition, we are moving away from coal and gas and steam and etc. Yep, that's fine. You can change that. So a little bit about our quantum team. So in order to address these challenges, the company I work at, which is specifically Eon Digital Technology, we have a department called Expert Services, where we employ almost 200 data professionals, data scientists, etc. And we basically build internal tooling capability for our company in order to leverage the latest technologies, data science, optimization, AI, etc. And here, what we spun out from this department is the quantum computing team. And so we've been active in this space since about 2020, going through our own quantum journey and onboarding the organization. And what our goal is to find real world applications that can deliver a quantum advantage to generate business value and generate a safer, more renewable energy grid and etc. So it's been quite a long 6 years going through the pandemic, and so like we all were, but we managed to have some nice accomplishments in this time. We have 26 publications on quantum applications, some various business problems throughout our company. We also hold several patents. We're partnered with IBM Quantum to get access to their fleet of quantum computers, and we also participate in government grants with local universities, nonprofit organizations, startups, all these great things to build up consortiums for real world business use cases. And on the right side, you see, if any are familiar with the Quantum Insider. So the Quantum Insider and Horizon X Consulting have a quantum index where they measure companies in different sectors and rank them kind of globally. And last year, we were ranked number 1 in the world in the energy and gas utilities sector for the work we've been doing. So that's our background. Mackensen, next slide, please.
Yes.
Yeah. Okay, so when we started the collaboration with Wiser, we had a pretty fundamental question. So I just showed you the energy demand and changing and all the beautiful solar panels. One of the things we need to do to correctly understand how much electricity to route to different communities and how much to buy on the energy market is, of course, we need to know how much energy people are using. And so most houses in certain countries are equipped with smart meters now. So this is for your energy bill. So this data gets sent up to the cloud. And in a way, one of the holy grail questions is, how accurately can you forecast with classical time series models or maybe some machine learning or, et cetera. It really depends on a lot of regulations. So this is really just like a scientific proof of concept, but we wanted to know, can we leverage the power of quantum computers in order to potentially more accurately predict what customer energy usage and consumption might be. This is a time series problem. And the thought process was, look, if we can come up with a couple novel algorithms and have them run at utility scale, meaning over 100 qubits, it could be that the novel quantum algorithms could be applied to many places because time series forecasting is ubiquitous in every sector across the world. And there hadn't really been too much research about predicting multiple time series at once. And so this is the use case. This is the real world challenge it's connected to. Basically, I posed this problem to the team at Wiser and gave them this data that we see here. So this is some anonymized real-world customer data from somewhere in Germany. And you see that this is a period from 2017 in this snippet. It's quite old, but you see the kind of energy usage going up and down. And okay, maybe on those days the house was kind of turned off. There's not much. Maybe that's the refrigerator running. But here you see the energy spikes. So this is what we gave them. And a couple ideas of some quantum models as a challenge to work on and say, okay, let's see what we can do. Can we create a quantum model or multiple quantum models? It needs to run at 100 qubits to make it utility scale, which makes it into, depending on the circuit complexity, a classically hard regime to simulate. And let's see if we can predict multiple time series at once. And with that, I would hand over back to you, Mac and Sunny, to start discussing the results. Okay, I can say one last thing. So we have a paper. Here's the paper. It's on arXiv, and if you search any of our names, it'll come up. But Mackinson, you can take over and explain.
So the quantum algorithm you use, in this case, the quantum Gaussian process and quantum reservoir computing to forecasting these data set that we show later. And also to improve this goal, we are investigating some specific topic, for example, mitigation error, and also the exponential concentration that we can find in a scale experiment using quantum hardware. And we try to improve the error mitigation in order we can have better results. The model can predict with better confidence. And I will invite Aditi that will speak about how we can benchmark quantum advantage or looking for possible quantum advantage and real-world data set.
Sure, thanks. Okay, so before we even talk about what models we worked upon and get into the intricacies, the first question was, when can quantum machine learning actually outperform classical machine learning? So the figure that you see here has 3 sections. Now, the smaller circle that has BPP, which contains problems that efficiently get solved by probabilistic classical algorithms. Then we have this larger circle that's the quantum region representing BQP, which contains all the problems solvable efficiently on a quantum computer. Now, since BPP lies entirely inside BQP, every efficient solvable classical problems can also be solved by a quantum computer. Now, on the right, when you see, we have machine learning algorithms operating on data. Now, their performance depends not only on computational complexity, but also on the information contained within the data itself. Now, this means that in many particular settings, classical machine learning can perform, Mackinson, the previous slide itself. I'm not finished. Slide 10, the previous slide.
Slide 10? Okay.
Yeah, that's fine. Now, having said that, this means that in many practical settings, classical machine learning can perform just as well as quantum machine learning, particularly when sufficient high-quality data is available. Therefore, the objective here is not simply to replace classical machine learning with quantum machine learning, but rather to identify the types of data sets where, quantum representations may capture useful structure that classical approaches usually struggle to learn. So now this naturally leads to the next question. How do we determine whether a particular data set is actually suitable for demonstrating quantum advantage or not? Next slide. Now, this question motivates one of the central ideas behind our work. Now, instead of assuming that quantum machine learning will always outperform classical approaches, we ask 2 questions. The first is that, does there exist a data set where quantum machine learning significantly outperforms classical machine learning? And second is, if we simply provide enough training data, can classical models eventually generalize just as well? Now, our work investigates these questions using kernel-based learning methods, where both classical and quantum kernels are evaluated under a similar framework. Now, one of the key observations from our study is that the effectiveness of quantum kernels depend heavily on the structure of dataset. Particularly, we use the concept of geometric difference that I'll be speaking in the next slides as an indicator of how differently quantum feature space represents the data compared to classical representations. Now, after this motivation was identified, we automatically understand what data sets we're using and how we are using in the experiments. So yeah, now On the left, let's look at the left first of all. Now, on the left, we show representative daily electricity consumption profiles from 3 different customers. As expected, each customer exhibit distinct usage patterns over time, reflecting variability commonly observed in real-world energy demand. Now, on the right, when you see is the overall dataset organization that we did. We chose 15 highly correlated customers from the 103 customer dataset that we had for detailed experiments. Now, these customers were then organized into different groups and random triplets for evaluating the forecast algorithms. Now, the figure here also distinguishes between the experiments that were performed using quantum Gaussian process, that's highlighted in the blue, and then kernelized quantum reservoir computing with repeated measurements, that's below in yellow. Now, this experimental design that we had allowed the models to be evaluated across multiple customer groupings rather than just relying on a single data configurations. Next slide, Mackinson, please. Yeah. So see, so far we've discussed that quantum advantage depends strongly on the data self as well. Now the next question is, how can we objectively determine whether a data set is likely to benefit from quantum machine learning? Now, rather than relying on prediction accuracy, we use 3 complementary tests proposed in quantum machine learning literature. The first one is the geometry test. Now, here we compare similarity structure created by classical kernel with that created by quantum kernel. Now, if both the kernels represent the data in almost the same way, then classical machine learning is just expected to perform similarly, and there is little reason to expect a quantum advantage. Now, the second is the complexity test. Now, this evaluates how efficiently classical and quantum models can generalize from available training data. In other words, it examines whether one model requires substantially more complexity than the other to learn the same prediction task. And then we had the dimensionality test. Now, this measured the effective dimension of the quantum feature space, meaning a richer feature space can represent more complex relationship, but it also must remain learnable from the available data. Yeah. Now, this slide here presents the experimental validation of the theoretical ideas that were presented. On the left, that is the A figure that you see, shows the geometric difference that's denoted by GCQ as well between the projected quantum kernel and classical kernel, that's Laplacian kernel, as the dataset grows. We observe that the geometric difference increases approximately linearly with the square root of the data size. This indicated that as more training samples become available, the quantum feature space becomes increasingly distinct from the classical representation. And then for the second image compares the effective model complexity that's represented by kappa across several classical kernels, including rational, quadratic, RBF, Mattern, and Laplacian, and then the projected quantum kernel. Now, the shaded region that you see around the quantum kernel represents one standard deviation across repeated experimental runs. Lower values of kappa correspond to simpler effective model for the target prediction task. And together, these results just suggest that the projected quantum kernel constructs a feature representation that is geometrically different from classical kernels while maintaining a competitive effective model complexity. So, yeah.
Okay, thank you.
Over to you. Yeah.
Okay, now we will discuss one of our quantum algorithms, that's a multiple output quantum Gaussian process. The idea behind this quantum algorithm, as we know, a quantum Gaussian can be used a classical kernel to do prediction. In our case, we use multi-output, and instead of using the model to predict from one customer at a time, you use a quantum multi-output quantum Gaussian process and to predict for multiple customers at the same time. Two components of the quantum Gaussian process is the kernel. In this case, we didn't use a classical kernels or a fidelity kernel. You use specifically a projected quantum kernel. How we construct this projected quantum kernel? In this case, we use reduced density matrix to extract information and locally using true qubit projected. After that, we measure the quantum secret. We get a binary string for each case or for each input data. with this bin string, we calculate the expectation values of use and use these expectation values to get the projected quantum kernel that is a key component of the Gaussian process. In this case, the circuit you use to construct this projected kernel is a hardware efficient feature map that in this case you use for 5 customers. And this first we start by encoding the dataset and each qubit. And this case we don't encode in one data point and one qubit. We encode a vector data. In this case, a 50 hour energy consuming by each customer. After that, we use entanglement layer in order we can extract information between the coded dataset. In this case, this model can effectively predict for next 12 hour or 15 hour and using our algorithms. So as we can see, the results we get using the smart demonstrations using the multi-output quantum Gaussian process. And this model is not only do predictions, but also quantify the uncertainty associated with this prediction. Instead of using only the prediction, you can ask the question, how confident is the model predicting this energy consumption? After demonstrate this, the model is working for a smart dataset or a smart experiment. Now we will introduce a scale experiment where you use more 100 qubits. In this case, the idea behind this project is to develop a quantum machine learning or quantum algorithm in order to take advantage, maybe to do prediction for an intercities with many households. In this case, we scale the experiment using a 100 customer dataset. As we can see, we have this is the same architecture for the circuit. In this case, you use a 100 qubit. After transmitting, we can see in quantum hardware, the circuit change a little to map with the available qubit we have in the quantum processor. So after mapping this, as we know, the challenge of quantum algorithm is to map the information to quantum processor. And we've associated with noise. In this case, you plot this graph in order to show the distribution of errors and the passing time and the quantum hardware we use to process the information. In this case, you use IBM Marrakech processors. And when we have the green color, that means we have low noise between the connection between two qubits. In this case, the CZ gate error, and the red indicate we have high error distribution between these two qubits. That means the operation is not perfect. Sometimes we have noise, certain noise, and the quantum operation. So as we can see the results we using 100 qubits that correspond to 100 customer dataset at the same time, using the entanglement layer between the dataset in order we can take advantage of correlated information between these customer. In this case, the result we present previously using 5 qubit is outperform our classical baseline. Regarding the scaling experiment, and we do an analysis. In this case, we have 100 customer. And this table, we can see we divided the error in 3 parts: low error, medium, and high error. The results we get, more of 7. The predictions is between low and medium error. That means out of the error we get from the quantum processor, we can predict with confidence 70% of correctly the dataset. That means if you have 100 customers, we can predict with confidence for 70 or more customers. So I will invite again Dr. Koi that will speak about the second quantum method we use, that is the quantum reservoir computing.
Yeah, thanks, Mackinson. Great. So the paper, as we said in the intro, looks at two different kinds of quantum models, right? Atkinson showed here how using projected quantum kernels, we were able to scale it to use real IBM quantum hardware using 100 qubits to predict 100 different time series. And so that's really nice scalability. It's very challenging to get things to work with 100 qubits and have them entangled. Circuit design plays a huge role. Actually, that was probably the majority of the project, was figuring out a trade-off between the accuracy and the complexity of the circuit in order to get it to scale to 100 qubits and have it trained, because that was ultimately a variational quantum circuit, and anyone who's tried to train those before knows that there's inherent problems there. For projected quantum kernels, this is a phenomenon known as exponential concentration. There's a really nice Nature Physics paper about it, Nature Physics or Nature Communications paper about it. And so we were sort of battling that, and we had to turn on all the bells and whistles of the IBM hardware in order to get it to work reliably at this scale. The second approach is what I'm going to talk about now, which is about quantum reservoir computing. And the neat thing about this is it is not a variational quantum circuit. So you avoid a lot of the problems that's inherent to training a variational circuit. And we based our architecture on this diagram here. There's a link below to the archive paper. The original paper was done by researchers from Keio University in Japan, some collaborators in Australia, and they designed a mid-circuit measurement protocol for quantum reservoir computing such that you have a memory in the kind of circuit. So I'll explain what this diagram is. It looks complicated, but it's really not so complicated. So the idea is, starting on the left-hand side, you have a time series of data points U1 to UL, and you load them into a unitary block. So U of U1, so you take the first time series data point, you put that in. On the right-hand side, in the upper corner, you see what the sort of circuit is here. So you have some blocks of some RX rotations and some C0 gates doing the entangling. And this makes your reservoir, okay? And what you do, going back to the left-hand side, you have this green block. So you have your data point loaded, then you entangle it down below to an ancillary register. So just means a bunch of different other qubits that you don't touch. And on that register, once you entangle it, you do a mid-circuit measurement. So you measure the Z basis, and then you reset the qubits back to 0. And then on the top chain, you don't touch those qubits with the measurement. You continue evolving that state coherently, and then you load in the next data point, U2, in your time series. Okay, and then you entangle that down with your bottom register. You measure, you get out those numbers, essentially, right? And so you keep track of your mid-circuit measurement outputs. And the idea behind it is that your top circuit has a memory, right? So it's sort of somehow decohering, right, over time, but you keep kind of pulsing it and loading new information into this. And the original paper goes through and shows that there is a memory effect, and you can tune your circuit to have varying amounts of memory. So this is great, and this is only for a single time series. And what we wanted to do was, how do you generalize this to multiple time series, right? So if you go to the next slide. So this is the same picture we just saw here. So you have your block in the top, your encoding unitary for X at time T. X is a time series. And then below you see a 2-qubit gate, which entangles it to an ancillary. It's a register, but it's drawn with a single line, okay? And now if you click next, exactly. So now you see we've extended the whole register, which is a good thing. We have access to quantum compute chips that have 156 qubits, because you can imagine this requires a lot of qubits depending how many time series you want here. So what we've done in red is we've entangled the reservoir register, Q1, with the next reservoir register for the next time series, okay? So the first one, so you have the diagram I just showed, and quote unquote, all we're doing is entangling the reservoirs together in a chain. And yeah, maybe it sounds easy, hopefully, the way I explained it, but here you see, again, the zoom in of the block, of the U encoding block. where that was a hyperparameter we had to play around with. So we had to see, okay, how big should the encoding register be? And what you see interesting is in the bottom plot, we called it number of qubits per customer, right? Because we're trying to forecast multiple customers time series at once. And you see, which is a good thing, that entangling these blocks produced lower error. So somehow the information is sort of working together in a way. And the quantum reservoir is able to understand the sort of connections and nonlinearities between the time series. So we're sort of combining all the lagged values of all these different time series. So that's one nice result of the paper. And if you go to the next slide, we show a snippet of one instance of our utility scale circuit. So this is before transpolation, where we check the gate depth. And if you click next, there you see the part of the circuit where you see we have the transpiled circuit to Marrakesh chip. And for those of you that have been running on IBM hardware, here's the technical details. So for this, we ended up using, I believe it was 15 lagged data points. I just saw a live question. So it was 15 data points as training data in the time series, and we're predicting the next 5, okay? And we did it for 3 time series at once. And the reservoirs were 15 qubits per customers, and the ancilla register was 15 per customer. So it was 30 qubits per customer. So that was 90 qubits in total. And with 90 qubits, that's for the raw circuit. And then once you transpile it due to gate connectivities in the chip, we ended up getting to 114 qubits. I have a typo here. It should be 114 qubits. The total gate depth was 114. The 2-qubit gate depth, which is the relevant metric for running on IBM hardware at least, is 51. So this is a good regime, but it is definitely a size that needs error suppression and mitigation. And so that's what we also turned on here. So we used, for those that are familiar with Qiskit, we used the sampler V2 primitive here, and we did XPXM dynamic decoupling sequences, and we also turned on polytwirling on the gates, on the 2-qubit gate operations with 32 randomization hyperparameter setting for the error mitigation technique to get the final results. Okay, next slide, please. So here you see a graphical representation on the chip, which qubits were chosen. You can see up to 0, up to 115 were highlighted here with the live calibration data from the machine at the time of the experiment. You can go next, please. And the final results were interesting. So using the 114 qubit, we ran it with matrix product state simulator, just a native one that comes in Qiskit Air package. And we got that using MPS, we got a 36% improvement over the classical baselines. And the classical baselines were 2 in this case. So we had the closest classical equivalent to this model, which is an echo state network combined into a kernel regression model. So there's a bit more details to the model I'm not going into. You can check the paper out. But essentially, once you measure the outputs from the quantum reservoir, you create kernel matrices and feed this into a kernel regression model for each time series. And then we also compared it to a naive baseline, which is essentially kind of taking the last known data point, which is the most kind of correlated, which is generally true with time series forecasting. And here you see, oh, sorry, go back. So here you see that for a couple customer IDs, it did pretty well, but for some of them, I mean, this is just one example. There's more details in the paper. But overall, the MPS, which shows, okay, it was run with some bond dimension so that we could get it to run and be simulated. But when we ran it on the hardware, it ran, it's fine. We got real signal out of it. But of course, the quality was degraded, right? So the performance was degraded. And then in the end, the quantum hardware was slightly worse than the classical baseline. So we went from 0.8 MA to 0.1. So that was a good thing that we were investigating multiple time series forecasting models, but still very interesting result that at least with MPS, as quantum computers get better and can handle higher gate depth, we can still squeeze out some nice performance on that. Okay, and then the next slide, I believe, just shows an example of the output. So you see, we're talking about these errors, right? 36% improvement and 0.08, and the quantum hardware did worse. But I mean, if you just look at an example, this is just one of the windows in the test set where you can see the train data coming in, and then you see the test data with the 5 outputs that are predicted all at once, the quantum simulation and the quantum hardware. I mean, visually, they're all pretty close, right? So it's not noisy, and it's good no, it is noisy, but it's not pure noise that came out of the quantum computer. So we consider that a success, and it's one of the largest time series forecasting experiments done as far as I'm aware, at least for multi-time series, multi-step forecasting. Okay, then next, I believe I'd hand it back to you, Mackinson.
Thank you. I think after presenting the results we get from this project now, we have some future research topic we will include in this project. In this case, the first is using advanced error mitigation. As we can see, when we map the quantum algorithm to quantum hardware, you can see some distribution noise across the qubit, the entanglement qubit. Maybe it's a good idea to develop a advanced noise error mitigation, and another we can mitigate the noise that present in this quantum algorithm, and we can get a better result. The prediction can be with more confidence. For example, in the multi-output quantum kernels, we can see 70% of the customer we get a good prediction, but using advanced quantum error, we can get more 90% of the results may be useful to take informed decision regarding the energy forecasting. And also maybe we can work to reduce the kernel complexity, for example, to reduce the execution time of the quantum algorithm, because the idea is not using a little number of customer or few number of customer. The idea is to build a quantum algorithm or hybrid quantum algorithm to predict for more 100 customer or one city in this case. Also, regarding the quantum reservoir computing, we will optimize the NCR qubit maybe in this case we can use more customer data set to do prediction at the same time. So as we can see, we have promising results that show the quantum algorithm or hybrid quantum algorithm can be useful in energy sector, where you can predict for complex data set or for multiple customer at the same time. And also we introduce how we can demonstrate quantum advantage and dataset. The quantum advantage is not assumed, but we have to demonstrate the quantum advantage of a classical algorithm using maybe some specific dataset. As we know, we can get quantum advantage in almost the sector, almost the dataset, but we can get some quantum advantage in specific dataset for a specific use. Also, we can see to the future research, we can include in the advanced error mitigation method in order we can scale more our quantum algorithm to another maybe can be the company can use it in practical application to take decisions to energy production and etc. Okay, how we can see the paper we have, the hybrid quantum classical machine learning algorithm for multi-output time series forecasting at utility scale. This is the paper that we write for these results we get in this project. Also for the data calculation of quantum advantage, you use this reference paper, is Power of Data in Quantum Machine Learning. Thank you for your attention. Now we open for our question or discussion. Thanks.
Thanks, everyone. Yeah, so I'll go over a few questions. I see already that some have been answered by Corey, by Aditi, but some have not. So one of the questions is, do you see pure QML becoming practical for grid operators within the next 5-10 years? Or do you think hybrid quantum classical approaches are more likely to be the practical path forward?
Pure QML versus hybrid approaches. I guess by pure QML, they mean just a variational circuit, I suppose. I think there's more promise in hybrid methods, actually. So either using, underlying what both of these models are is, I understand it's a bit technical and hope everyone kind of followed through. But the paper, I've shared it and we'll share it again here in the chat now. I encourage you to take a look at the paper and upload it to ChatGPT and ask to summarize it and any other questions that you have, which is the way it works these days, or reproduce the code, right? But under the hood of these models is something interesting, is that using quantum computers is essentially feature extractors. So the core of the model, of both models here, was quantum, running on a quantum computer. But at the end of the day, what we did is we measured expectation values that come out of the quantum computer and then somehow, in a way, post-processes them into a downstream or an outer loop classical process. So there was a question here, how did you get the uncertainty bands that Mackinson was showing? So that comes from the definition of a Gaussian regression model. And so that's actually what we did. If you look up what a Gaussian regression model is, there's a part inside where you build a kernel matrix, and we basically just built this kernel matrix quantumly, but the whole rest of the training of the other parameters of the model is done classically. And if you just take a step back and again, just look at a high level, it's just loading the data into the quantum computer, manipulating it in some higher dimensional vector space, projecting it down to get some new numbers, right? And then from those new numbers, you pass it into a downstream application. So I think that this is going to be the future of quantum machine learning. Whether you use that in operations is a whole other question. So something that we've been taking more seriously now in our quantum journey. The next question is, what do you run in production once quantum computers are available for production? So very few vendors, I think D-Wave might have one for quantum annealing, but I don't know of anyone else that has service level agreements. So if you put something in production in the real world, these machines have to be available and the queuing has to be fine. And, so there's opens up a whole other can of worms of questions about what does it mean to have a quantum computer running something in production, and also the cost. So just because we get a 2% better forecast or 5% or whatever anyone will do for any time series or any quantum machine learning empirical advantage, okay, what does that translate into? Money, and you got to pay to run on the quantum computers, and they're not cheap. So that's a whole other thing. And right now for this study, this is definitely an important business problem for our company. It is a broad enough topic that it should be good for the community to look and see, hey, these models have been scaled to utility scale. And so that's sort of the broad answer to that question.
Great, thanks, Corey. There's another question that just came in. What is used for the regression of Z expectation and how much accuracy is lost? Is quantum part is removed?
So again, there's two models. So in the quantum reservoir computing one, that was Z expectation values. Yeah, that was just local Z in the Z basis on every qubit. And on the other one, Mackinson, you have to answer it. That was a huge part of the paper, by the way, about finding which expectation values to use. We actually got the best answers when we did almost full process tomography. So, but I mean, this doesn't scale, right? So when you try to measure every Pauli basis element between 1 and 2 local pairings, let's say, this induces a massive amount of overhead when you want to run something at utility scale. Again, going back to what the trade-offs were in the project, but Mackinson figured out a way how to do that. So maybe Mackinson, you can explain a little bit which expectation values you used.
You're on mute, Mackinson.
Okay, I see a question about uncertainty and the forecast. We use the quantum Gaussian process. The uncertainty is one of important component of quantum Gaussian process. Is where is the confidence, how confident is the model to do this prediction. And this case is the prediction do between a space, maybe minimum and maximum point, and the model do the prediction between these two minimum and maximum point. This is the uncertainty quantification. And decision making is very useful because not only we calculate the risks of taking this decision using this prediction. It's a probabilistic point of view, so the quantum Gaussian process in this case.
Mackinson, can you talk about which expectation values you used?
I can't echo the words, but what do you say? Can you repeat, please?
I think the question was, what is used for the regression of the Z expectation and how much accuracy is lost if the quantum part is removed? So we were talking about the expectation values for your projected quantum kernel. You ended up doing 1 and 2 local X, Y, and Zs, I think.
Okay, in this case, I use the full probability basis. In this case, ZZ, XZ, and we use 9 probability basis. And there is, yes, 9 probability basis after committing basis. For that, we have many measurement and the projected quantum kernels.
Great. We have time still for some questions. There's one question that says, can you explain more about the final data after pre-processing and before feeding it into the reservoir computing circuit? How many samples exist, and for each sample, what are the features?
I can't tell you off the top of my head how big the training set and the test set were, but we basically had time series data from a full year, and we ended up looking at the seasonality of the data to, I believe, predict either only the summer or only the winter. It's been a while since we wrote the paper. So we basically looked at a single season and then created the train test split on that. But yeah, you'll have to see the paper for exactly the size of the training data. And what was the second part of the question, David?
Just realized. Can you explain how many samples exist? Is that one you answered? And for each sample, what are the features?
Yeah, right. So the features were just lagged time. I mean, each model was slightly different. So you put in lagged features basically. So we didn't calculate any statistics on the data. We didn't use date time features. We didn't use weather data. We didn't do any of those things. So it really was a very basic model. You take a set of time series and you take the last values of that time series and you try to predict the next time values of all those time series. That would be future work that we'd like to explore about how to generalize it to using weather data or one-hot encoding, daytime features and things like that. So very, very initial steps here, but it was hard enough to get working with 100 qubits.
Great, thanks. And we still have 3 minutes, so I think this could probably be the last question. Can you give us a real example where QML has actually performed better than XGBoost, LSTM, or transformers for energy forecasting?
I think it depends on what it is you're trying to benchmark. So you forgot to mention random forest, my favorite classical model that basically wins all the time, but also boosting models. So yeah, you're right. As far as I'm aware, no one has claimed any quantum advantage across all of the models. Typically, what we do to not open that can of worms is to compare like models to like models. So in this study, we fairly benchmarked and compared the also hyperparameter tuned versions of these quantum algorithms. So Mackinson did quantum Gaussian process regression, and we compared that to the equivalent classical model called Gaussian process regression. We also compared it to the naive kind of baseline, which is just a very simple lagged time step, take the last value sort of thing. And so that's kind of what we did here. We've done some other works where we've expanded it and kind of checked, all the basics like LSTMs and transformer models or foundation models are interesting. We are working on that in a separate project. I can't say too much about it, but there seems to be some very interesting results there when you start talking about foundation models. But yeah, no one has claimed quantum advantage for this area generally for quantum machine learning. But I think that it's definitely an interesting avenue to research.
Perfect. Thank you so much for answering the question. So just one final thing. So thank you to all the speakers. First things first, for being here, for presenting the case. This is really interesting. Quantum, as you can see, keeps moving forward. Maybe someday we'll see this actual advantage that, Some claim, some others don't, but I'm sure that the technology will advance like many other technologies in the past and others in the future. And just one last thing. So if anybody from different companies are interested in collaborating with Wiser on a use case, please contact Prachi, who's our founder, and also soon she will be at Q2B Copenhagen. So if you are going to be here in Copenhagen at that event, feel free to contact her or add her on LinkedIn and reach out to her, and so you can have a coffee meeting at the event. So thank you very much, everyone. Really appreciate everybody for attending and for asking the great questions, and for the speakers for being so great at doing what you're doing, right? So thank you so much again, and have a nice evening, day, wherever you are on this planet. All right.
Thank you.
See you,
Bye-bye.
everyone.
Thank you, everyone.
Thank you,
Bye.
everyone. Bye bye.
See you.